Hello, everybody. So today we are going to be talking about some of the more advanced topics with valence bond theory. So specifically what we're going to be doing is extending the ideas that we developed last time for valence bond theory to second row elements. So here comes the p orbitals. So when we're going to be doing this, we're going to start with a quintessential diatomic molecule, nitrogen. So specifically nitrogen gas. So we've got two nitrogen atoms put together to make a single molecule, which means, guess what? We need to start by figuring out what the atomic orbitals are for each of these atoms. So each of our nitrogen atoms are going to have the same electronic structure. So we got a helium, but this is valence bond theory, so we don't care about the core. And we also have two s electrons, but this is valence bond theory, so we don't care about the non-reactive or partially filled orbitals, or fully filled orbitals. So all I care about is the partially filled orbitals, which means our main interest is going to be the fact that each of these nitrogen molecules has a single electron in each of those three p orbitals. Now, here comes the trick, because back in Gen Chem, we didn't know any better, and we said, hey, px, py, and pz. In this case, we're still going to be using those orbitals. And the reason why is because valence bond theory is a visual technique. So it cares about Cartesian space. So I'm going to be caring a little bit less about my about the eigenfunctions of my directional angular momentum. So we're going to put we're going to be treating just our unfilled electrons, and we're going to be looking at how these three orbitals are going to overlap to make bonds. Because again, in valence bond theory, the bonds come from overlap. And as I said before, we're going to focus in on our px, our py, and pz orbitals. So each of these have one electron, which means I'm going to have three bonds, one from the overlap of the pz, one from the px, and one from the py. And again, each of these overlaps will dictate the strength and type of bond. And that's what we really care about. So let's go ahead, and because I care about stability, we're going to start with the most stable of these three bonds. And that is going to be a direct overlap. Because as we saw before, the higher degree of the overlap, the more I'm going to draw these two atoms together. So a head-on direct overlap is going to tend to be the most stable. And we can look at this visually, as I'm going to have my two p orbitals overlapping to make a bond. And by the way, before I forget, I do want to make a point. All the pictures you've ever seen of the orbitals of a second row element are probably wrong. Because don't forget, these s electrons are going to be way out here. We're still going to be treating them like core and hoping that they don't interfere, or more specifically, that their overlaps don't matter. We'll get to that more later when we're talking about molecular orbital theory, but I want you to keep that in mind. But again, our most stable overlaps are going to be these direct heads-on, because they're going to build up an extra degree of electron density in here, which is going to attract both of my nuclei. And this is what we've been thinking about in valence bond theory, is forming a strong bond. By convention, the two orbitals that overlap are going to be the pz orbitals. This can be any arbitrary orbitals, but by convention, we always treat the direct head-on overlap as being done in the z-axis with the pz orbitals. So if you hear me talking about pz orbitals, especially in valence bond theory, but even as we move on to MO, don't be too surprised if we're talking a lot about these direct head-on bonds, which is more or less going to be given the same name it was when we did it with hydrogen. They look like s orbitals, they're sigma bonds. And their wave function is going to be very similar, because since these are direct overlaps, this means that we are going to be having an additive wave function. The orbitals are going to be building up in intensity, so we'll be looking at the symmetric combination considering both of the options where the first electron is on the A orbital and when the second electron is on the B orbital, and then of course the switch, which I did not include here. I apologize. But again, this will be the same symmetric switch, but because my wave function is symmetric, this means that my spins have to be opposed. My spins have to be anti-symmetric to allow Pauli to be satisfied and have a symmetric wave function. So when we do this, what this means is that my electrons have to be paired. That's what that asymmetric wave electron spin meant, if you remember when we were looking at multi-electron atoms and the singlet case. So congratulations, we have a singlet orbital because my spins are all paired up while the orbitals are also adding together. So we have a spin paired system, building wave function. This is what defines a stable sigma bond. However, we still have two sets of orbitals left. We've got that px and the py orbitals. So it turns out that the px on each of the centers can overlap, but it turns out that the easy option was already taken. This head-on option, it's gone. PZ won out on that, which means that all that's left is these oblique overlaps both above and below. And so this is going to form my new most stable bond. And so you have px doing this in one direction, and in nitrogen we also have an empty pz, so it will occupy the separate direction. So we're going to have two of these sets overlapping with each other. Now, because if I look down this bond, this is going to look like a p orbital. Go figure. So early chemists, being the creative sorts they were, just like with the sigma bonds, decided to name this P, except in Greek. I introduce to you the pi bond, and it's going to have a very similar wave functional form, where I'm going to have first electron on atom A, second electron on atom B. You switch this, and because they have a direct overlap, the two wave functions are lined up in phase instead of out of phase. We have the symmetric combination. But again, because I need to satisfy Pauli, it means that if the electrons are if the orbitals are lined up, then the spins have to be counter-aligned or asymmetric. So we end up with spin pairing, up electron with down electron and down electron with up electron. And so we can have one pi bond in the x direction and one in the y. And so when we put this all together, what we end up with is going to be a set of in-phase combinations, both in the x and the y direction, to get two pi bonds with the aligned spins, with again an overall singlet system. All right, this should hopefully make sense. This is what we're after. We're trying to use our valence orbitals to figure out how we can line up our atomic orbitals to make a bond. And in this case, because we want a stable system, filled low energy, everything should hopefully end up as a singlet case. We'll occasionally run into cases where this where this won't happen, but in general, valence bond theory will do a poor job of predicting it, because valence bond loves closed shell singlets. So we're going to be seeing a lot of these, and we're going to be seeing a lot of in-phase combinations. These are the characteristic features of valence bond theory, and will occasionally fail. But to remedy that, we're going to have to go to MO theory. However, next, we're going to take a little bit of time to talk about systems where treating everything as single wave functions that I can add up to give a net molecular system doesn't quite work out so well. So next time, we're getting into the nitty-gritties. Take care and stay healthy.